Thanks for coming, everyone. Hopefully you find this to be both fun and informative talk. We're going to be focusing on the magic of data science and the fact that we've actually been predicting things as human beings for a very, very long time. It's just only recently that we're moving some of this magic into data centers. How many people right now are actively working in data science? About a quarter of the room. How about maybe not purely data science, but machine learning? About the same? How many people would like to? A little more. So it seems like we've almost got consensus. Well, we're going to talk a little bit about, the types of things that we like to achieve with data science, some of the things that go wrong, and then hopefully steer it into some of the things that go very right. So, music recommendations. How many people listen to music? Oh, anybody that doesn't raise their hand has to leave. No, joking. Especially if you don't listen to Rod Stewart or Kenny G. But let's say you do listen to Rod Stewart and Kenny G. Now let's say I'm developing a music recommendation system. What I'm actually going to do is encode my own intuition into the system now, likely using, if I don't use data science or machine learning, using decision trees, perhaps a lot of if statements. And perhaps because I happen to like Rod Stewart and Kenny G, I also like a lot of other bands, and perhaps my decision trees are going to lead you to napalm death. Can we do better than that? Well, what we're really trying to do is get an idea of what you may like without us having to hard code this. So your affinity to rock may be a 0.89 based on some of the subgenres that you also have a strong affinity to. Now, if we decide to implement a music recommendation service without data science and ML, this is probably what I'm going to spend a few years on, is one big long if statement. How many people have seen a really long if statement? How many people never want to see a really long if statement again? Okay, so this is what we're talking about. We're talking about a more effective and a much more fun and intuitive way of building out various types of predictions. And so really all we need, at the bottom, the foundation of data science, is having some kind of objective. Like, now if we want to suggest music to people, we're probably not doing this out on the street. Perhaps we have a business and we're figuring out how recommendations fit into that business. But once we have a really solid business objective, we need some data scientists, we need some data, and we need some engineering. And once we have all of those magical ingredients, we're ready to build something that has an 85% chance of failure. So according to Gartner, currently data science projects are tracking in at about an 85% failure rate. And it's not technical. I think at this conference especially, there's a lot of really talented folks that can really implement a lot of interesting and beneficial problems to solve these. So what we want to do is track all the way back to what's causing this failure, and how do you ensure that the next project that you work on lands in the 15%. So in order to achieve our objective of walking through how to sort of steer out of that failure, we're actually going to really focus on the types of things that go wrong on a data science project, and then the actions that we can take to steer away from those common sort of chasms of failure. And what can everybody in the reactive community bring to the table? So one of the other things is everybody here has the ability to get involved and do some really cool work. It's just a question of figuring out what are the different needs on a project like this, and how can we all fit? So without further ado, I'm going to introduce Dana here, and he's going to go over 101 of machine learning.
Yeah, so we're going to focus on machine learning as an application of data science. And to get a basic understanding of how machine learning works, the concept behind it, let's start out with that history of human attempts at predictions. So humanity's had a long fascination and obsession with being able to predict particularly the future. And there have been a whole lot of different methods that have been tried. There have been a whole lot of chickens that have been disemboweled along the way, all sorts of stuff to try and figure out what is the future, deep insights, prophecies. A classical approach to this would be the Oracle of Delphi, right? So in this method, what you do is you take a deep fissure in the earth with some sort of toxic fumes. You take a high priestess of Apollo. You combine them together. You inhale the spirit of the gods, or at least your high priestess of Apollo does, and find divine inspiration to make prophecies. This approach hasn't really translated into modern practices. Access to a fissure is a bit of a problem. High priestesses of Apollo, I mean, if you think finding good data scientists is challenging, high priestess of Apollo, there's not enough programs out there. And lastly, I mean, we do run into some problems with modern labor laws with some of this approach. So it doesn't really carry over. Am I not advancing here? Uh-oh. Predicting the future slide.
Yeah, I think this is what happened. Give us one moment.
Yeah.
Oh. Somebody else we've been signed out. So can you sign us back in? I'm going to unplug this for a moment. This is what happens. So like one of the common causes of failure in machine learning systems is when you anger the gods of data science, and then you can't even finish your talk.
And they sign you out.
Yeah, pretty much. So let me get us plugged back in.
Let's find where we were. Here we go.
Are we back?
Okay, so more modern approach, a bit more amenable to technology, would be expert systems. And whoa, what am I doing? I'll let you.
Yeah, maybe I'll steer for a moment here.
So expert systems. The idea with expert systems is you take a bunch of human experts in some sort of domain, you collect up a bunch of knowledge they have and a bunch of rules, and then you store that in some system that can evaluate that. So for our music problem, we might take a bunch of experts in music, particularly in musical tastes, and we would get them together and we'd codify all their knowledge. And what we find is that there's not experts that are experts across all genres of music. So we need a bunch of experts. And then we might have some listeners that are interested in more than one of those genres, so they don't fit into the domain of just one expert. And then we need systems of rules to decide which system of rules for an expert we need to go into. Never mind that music is constantly changing. We need to continually be manipulating these rules, adding new rules, evolving the process. It really doesn't scale up too well. So machine learning is the latest approach to this. And the difference is between what I just described in terms of expert systems and machine learning. In machine learning, we're using mathematics. We're using statistical methods to generate basically those rules. And we're doing it based on a bunch of data. So we're going to use algorithms to find those patterns, to generate those rules, to make our predictions, and automate that whole process. So the ingredients in this are the data. I mean, that is how our algorithm is going to get the insight, and it needs to be good. The learning algorithms, which are basically the mathematics that gets coded up into a process to extract that means of prediction, those rules out of the data. And then we need to take that mathematical artifact and turn it into something that runs in production reliably at scale, meeting SLAs. So what could go wrong? I'm going to see if advance me. I'm going to divide what goes wrong up into three different categories, and these are really going more fine-grained detail in terms of execution. So the first thing is the high-level objectives. Then in the approach and execution, which is really team problems, and lastly at the lowest level, it's technical problems. And as we mentioned, technical problems are usually not the biggest factors. We're not going to talk about those. If you manage to get it right up to that point, then you're nearly home free, or you manage to catch the technical problems earlier on because of the process you're following. So at the objectives level, this is really the elevator pitch, the concept, getting it right. And here, I'm going to use this image here of three worlds. What we need to do in order to be successful is bring together three worlds, three different disciplines, domains of experts in the business world to motivate our problem, the math world where our data scientists live, and then the technology world where our software developers live. And we need to get the problem framed right just at the broad level. So what we're going to be doing to do machine learning is take a business problem motivated by a particular business case. We're going to map it into mathematics so that we can solve it as some sort of mathematical optimization problem. And then we're going to map that back into the business domain. So there are things that can go wrong when you try and take an informal business process and you turn it into something very formal, run something, and then try and map it back. So in order to understand what that might look like, let's take another example. Let's say that we're in the business of giving out loans. So a key part of our business is I've got an applicant. Am I going to approve them for a loan, or am I going to deny them that loan? And we'd like to use machine learning to help us make that decision. Okay, well, I'm going to take a tangent here because we're coming up to Halloween and spooky stories are great, and I promise that this is somehow relevant to this. You're probably familiar with the story of the monkey's paw. How many people have heard some sort of version of the monkey's paw story? Right? There's lots of retellings. The original short story, I believe, basically the idea was there was an older gentleman who went into a shop and found in the shop a mummified monkey's paw, so that's intriguing. The shopkeeper said, it'll grant you 3 wishes, but I must warn you that you do not want to make these wishes, you will regret them. And the man, well, come on, 3 wishes. It's cheap enough, a mummified monkey paw. He takes it home. And the first problem he encounters is that he owes a bunch of money. He has mortgage payments or something to make. So he makes his first wish. And nothing happens immediately. The next day, he gets a call. There's been a fatal accident at his son's place of employment. His son has been killed, and the employer is willing to offer compensation to the father. That's actually exactly the amount that the father needed to pay off his debts. And so, there's 2 more wishes, but I'm not going to get into that. The message here is really, you need to be very careful what you wish for, because you might get exactly what you ask for. So, primed with that monkey's paw, let's say I phrase what I'm looking for is I want to produce an approval process through machine learning magic that what I want is it's going to deny any applicant that has a high chance of defaulting on a loan. Right? That seems great if I could use the patterns in the data to deny those people that are going to default, predict the future there, then it would greatly improve my business. Does anybody have any concerns with this? Yeah?
An algorithm that will deny every loan would satisfy this.
That's great. Excellent, predicting the future. Yeah. So this is exactly it, right? What we're doing is we're taking that problem, we're going to turn it, if we turn it faithfully into mathematics, then the mathematics is going to ruthlessly optimize with no human context around what makes sense at all in terms of your business. And this is an optimal solution, right? You're not going to miss anybody. You're guaranteed that everybody who's going to default, you denied. Perfect. Nailed it. Might be looking for a new job. So in order to set up this problem, really get it right at the conceptual level, there's a couple of questions that you can ask. Really nailing down what it is you're trying to predict, what it is you're going to do. So I want to predict who's going to default. What I'm going to do is if I think somebody's going to default, I'm going to deny them, and otherwise I'm going to approve them. And then how do I expect to be able to measure success for that? And that's actually really important for this. So I expect to see fewer defaults. I also expect to see that the number of loans I'm giving out doesn't dramatically drop. And what I think is really critical to get this right is to have as many different perspectives on the problem, different roles, different people within the business, as many perspectives as you can get so you don't miss those edge cases, so that you get the problem right and you start off on the right foot. And then we get into the next part, which is, great, we've nailed what we're trying to do. We have some confidence that if we do it right, it's going to be beneficial. How are we going to execute on this? I'm going to go into detail in this process, just sketching out what this might look like. But fundamentally, the problems that are happening here, a lot of them revolve around communication. You've got a bunch of experts, specialists in different areas that may not really understand the terminology and jargon. They need to coordinate very relatively tightly to make this thing work. And that's where a lot of the misses happen. And you may just have the wrong set of experts. You may have gaps that you're not aware of, or you're misunderstanding or misapplying the data. And lastly, that evaluation metrics. How do we know success? And that actually occurs in two different places. I mean, you can think of the previous slide as a lag measure, and what we need to do is figure out what lead measures are going to hopefully drive that, and code them up as math and hope for the best. So let's take another example where I might want to make a prediction. So I might want to predict real estate values based on some data I have. And in this process here, this is a very high-level view of what our team is going to need to put together. So above that dotted line is sort of the data science training world, and below that line is more of the application, the production model serving world, the online portion that's going to need to serve these predictions out at speed and scale. So loosely speaking, the first thing that's going to happen on that training track is we have a bunch of data. We're going to need to understand what's in that data, make some sense of what's there. Sometimes that's easier than others. Once we sort out an understanding of that, then that's the model training. We're going to do some sort of algorithm that's going to pull some insights out of that data. We're going to check to make sure that that model is good, that it meets the quality criteria that we have for success on that. And if it's good, we're going to publish it out, and we're going to hope to get this into production. And if it's not, we're just going to loop back and we're going to continue to tweak things until we meet that success criteria. So we need to sort out what needs to get done in this, who needs to do it, who has the skills to do those various tasks, and then what's really key here is what are the artifacts that are handed off between the steps in this process, and particularly some of those handoffs that occur between somebody coming from a traditional data science background and somebody coming from a traditional application background can be a bit challenging, but I hope we'll see that it doesn't need to be. So data engineering, I mean, we're talking about potentially collecting a whole lot of data, cleaning, validating that data, some data modeling, some transformations in that. And this is really where data engineers specialize. So we probably need a bit of that. We certainly need the data. Feature engineering is a task of taking that data that you now sort of understand and figuring out what parts of that data are relevant to the problem we're trying to solve. So in our real estate example, we might decide that some relevant features of a piece of property are the square footage, what neighborhood it's in, and if a building's on it, then how old is that building? There's almost certainly other things that are relevant to that, but we're picking out what are the properties that we're going to use to make our prediction. The next thing that's going to happen is is a bit more technical, and the team doesn't necessarily need to fully understand what's going on here. But I mean, we're going to start out by selecting a model. In the keynote this morning, we had some mention of that. We need to kind of figure out what shape of problem we have, and then what are our options for mathematical tools for dealing with that. So there's regression, there's classification, there's a whole bunch of these things. For our problem, regression is going to be the right choice because it is basically predicting continuous value, so something like money that's on a continuous scale. Once we've selected what type of problem we have, then we need to figure out what the approach is. So there's a whole bunch of varieties for regression of learning algorithms that you can apply there. There's linear regression and neural nets and various tree methods that'll get us there. So let's say that our data scientists, experiment around with the data. They do some POCs and that, and they figure that the best option for this particular problem is linear regression, right? Let's understand what that really needs to mean to the rest of the team who may be business people, who may not be data scientists. What do they need to know? Well, linear regression is really in the basic case, it's finding the line of best fit for a bunch of points. And so we're going to have some sort of equation that's in 2 dimensions it's a line. It's generalized to higher dimensions, and we're going to optimize best fit there. Then the training process, now that we've selected what algorithm, is taking data where we know what those features are, right? We know what the square footage is, but we also know what the answer is. So this is supervised learning we're talking about here. This is how our algorithm is going to find the right answer. We give it a bunch of examples with the right answer, let it churn through a bunch of stuff and figure it out. Oops. So what that algorithm is going to do is going to produce a model. And a model, machine learning model in this case, is really, for linear regression, is just going to be a fancy term for a bunch of numbers. If we had 15 different features, then it would be 16 numbers. So all that complicated process is going to produce an array of numbers, let's say, an array of doubles. And really what it's doing is it's finding optimal values for those parameters to match up with the data that it's been given, the examples it's been given. Now, there's a really important step and also a fairly technical step after that, which is seeing how good this model does. And unless this is your job, you don't really need to know too much about the details, but it is oftentimes really beneficial to understand the non-technical version of this. What it is that we're measuring about this to understand what's going on in this and how good a model is. What's our criteria? So to take an example, let's say for our loan approval, we don't expect our model to be perfect. It's not going to make 100% accurate predictions. I mean, if it does, great, but that's not reality. So there might be a difference for the business in different types of mistakes. There might be different costs associated to wrongly approving a loan when you really shouldn't have, versus denying a loan where you really shouldn't have. So false negatives and false positives. And that needs to be considered in the context of the business. So it gets coded up into math and part of that evaluation process. But there oftentimes is significant input in there in making the right trade-offs for the evaluation of those models. All right, back into this. So serving the models is basically, we generated a handful of numbers. We're going to send that off through Kafka or something like that. It's going to get picked up, and it's going to run in production. So what does it look like to run that in production? Well, this linear regression process with a bunch of math involved in it is just turning out to be a bunch of numbers. And what do we need to score that model, to serve that model? All we actually need to do is take a bunch of numbers that came from the training and a bunch of numbers that we have from the data, so the square footage and all that, those particular features for the instance that we want to make a prediction on. And in this case of linear regression, we're literally just doing some multiplications and some additions. We're plugging, substituting into a formula, and multiplying and adding. So the model itself is dramatically simpler than the process of training the model. And that's actually, I think, very much true in general for any sort of machine learning model, any training learning algorithm that I can think of. It's that, in this case, linear regression is typically a topic that's taught in second year university. The mathematics for getting that line of best fit. Whether you remembered or not, you probably have done the math for actually serving this model. It's typically grade school. You've got the equation of a line. When I learned it, it was y equals mx plus b. You might have seen a slightly different formulation, but you've got some variables. You've got values for those variables. You plug them in. You punch things into your calculator, and you get a number. So dramatic difference between the level of mathematical sophistication you need on the training side versus the serving side. Right? There's all sorts of tuning and whatnot, that tweaks we might do in linear regression on the data science math side to make this work. But really, we pop it over. We're doing substitutions and multiplication and addition. So that's not the challenging part. And just to see that, in general, we have other models that will, produce decision trees or collections of decision trees. And there's boosting and bagging and gradient descent and all sorts of fancy terms that go into there. And ultimately what comes out of there is our decision trees. Much like we talked about manually coding up earlier on, these are evaluate some Boolean expression. If true, then go on the right side, and if false, then go on the left side, and you're probably going to evaluate another Boolean expression. So basically, we've had the machine generate our massive trees of if-then-else statements here. So to summarize this team approach, there's a lot of steps. There is a lot of technical detail and jargon. You really need to understand what your role is. What do I need to know in order to be successful within this? And I think equally important, what don't I need to know? What can I relax and let some other expert, and I'm going to get a package handed off that makes sense to me. You don't need to understand everything. I'm going to hand it over to Kevin to talk about some things that we can do proactively to make sure that things go right.
This is like good cop, bad cop. So yeah, let's talk about how can we use what Dana talked about, some of the things that may go wrong. Like for instance, trying to teach everybody on the team, project managers, product owners, everybody linear regression, right? Like we've seen some situations of this just out in the industry. And it's great if you want to learn it. Actually, like apparently Mark Cuban took a little bit of time off and went and taught himself a lot of that just recently. But not everybody on the team needs to know the advanced math, and definitely not all of your data scientists need to become distributed systems engineers. So we're going to talk about what do the handoffs look like? What do we need to get right in order to smooth it out, let people do what they're really good at, and actually create really diverse teams of happy people rather than bogging everybody down on everything. So in our work, we have a consulting company called Red Elastic, and we've noticed a pattern. We've trained our model, and we can see some patterns in what goes right and what are the very easy steps that teams do, especially early on, to get things to get themselves into that 15% of success stories. So before we even get started, we need, as Dana talked about, now we're going to start getting into the operational side. So now imagine your mathematicians have done their job. They've fully aligned with the business objectives. Well, even to do that, I mean, you need a lot of raw materials. You need quite a bit of data, both real-time and historical, contextual data. The science side, Dana's talked quite a bunch about, which is exploration, hypothesis testing. And then where a lot of the people at the conference can make a huge contribution, which is on the engineering side. So taking all of the raw materials and building a finished product. So we'll go through sort of like the top 4 things that we see go really right on data science projects. Events. making a prediction on very, very stale data is usually far less beneficial than making predictions on recent data. You may need to take your recent knowledge and kind of join it together with historical context, but really what we're talking about is predicting the future, right? So leaning on events heavily in all phases of the process, we found to be a real predictor of success. And events are just things that have happened in the past and are interesting to the business. But they can't span all of history. We can have events in HDFS, or we can have events in Kafka, and they can be all sorts of different length of time ago. But they really are at the core of our analytics. So this is kind of where we see something that's very important, is we don't see a lot of the processes out in the market right now, especially agile, especially like stricter agile, being a really good fit with some of the rigor involved in the handoffs here. So we kind of have come up with a bit of a lightweight process on our end to ensure business objectives are really solid before even moving into the data science part. So one of our favorite tools for that is, how many people here work with OKR framework? Yeah, so we see this, you can look it up, but it's objectives and key results. So what's our objective and what are the key results that we need to see, and agreeing on those up front, having a handshake between data science and business on OKRs is really beneficial. But then when we get into the data science piece, it's still, we need events to be feeding basically every step of this process, because what data science is going to have to hand off is effectively a package that we'll talk about later. And obviously events are going to be very, very beneficial in the actual engineering and operations. But having a constant feedback loop through all of these processes is critical. And so one of the key things is part of this feedback loop is to understand the events that are interesting in the business. So we can say that we're going to build mathematical models on events, but oftentimes in a large enough business, we may not even know all of the interesting things that are happening within our business. So one of the things that we want to do early on is align on that. Do we need to actually take a step back at a much more simple level and do something like event storming? So go through all of the interesting business processes within our organization, map some of these objectives back to these, and this has been a very effective process for us during inception of data science projects. And why this is so important is because, back to our music example, we can start taking events, like let's say there's the obvious one would be somebody's listened to a song, but there's all sorts of other events that could happen, like is stopping or fast forwarding a song 10 seconds in different than 1 minute in, or perhaps we have certain data encoded in our songs, like, you know, in dubstep, a bass drop or something, you know, somebody keeps skipping past the drop. Maybe they don't like dubstep. There's all sorts of insight that we can gain on events, and not just the simple events, but all of the interesting events that we can think to get to these things like affinity scores based on the real-time behavior. So by the time they're ready to fast forward onto the next song, we already have a few good selections even based on what they just did. So part of this is you know, once we have events and we're all speaking the same domain language, we can really think about proper handoffs. And I'm not going to read all of this, but what I want to say is one of the, I think, key predictors of success is making sure, again, that your data scientists can be focused on what they do really well, which is exploration, hypothesis testing, actually creating a trained model. And this is one of the confusions, is that that's actually an optimal thing that they might deliver to the engineering team, is actually a trained model, and that could be in any type of format. Perhaps they serialize it and give it to you on Kafka on some kind of handoff topic, or it could even be they could even train it in Excel, a trend line. Right? So you could get all sorts of different packages, but the idea is that if you formalize this as a process, you can decide with your team what's the best type of handoff that you need. And So what we like to do is just have a very simple design doc process. So all of the assumptions and hypotheses and anything that's interesting to the engineers, what latencies are we expecting to see, things like this. And then we can turn that design into production quality code. And what we're really trying to get to is we might be taking that trained model in Excel or in any number of formats that the data science team will give us and create a training pipeline like this and be very specific on, you know, what's the training latencies, how often do we want to retrain and republish validated models. But there are some really critical pieces in this that I want to call out that are also another good predictor of success. So all the way back to the business objectives, and if you're using OKR format, you can make sure that key results are noted. So like, for instance, in the music example, we might want more active engagement in a broad sense, right? We want to see like 10% more completed song plays. Like, that might be a good metric to figure out if people like the recommendations, they listen to the whole thing. Maybe even they repeat the song. Now they love it. They're just really into this. So we can actually validate that model, see what's actually happening, and actually do that as part of the real-time system. So if we start to get underfitting or overfitting, we can actually catch that, and I'll come back to that a little later. But ultimately, what we want is not just a trained model, but we want a validated model, and there's some formal ways to validate models that we'll talk about. Ultimately, that model can be published. It can be serialized as an mLeap bundle and published to Kafka and ingested by the next piece of the puzzle, which is your model serving pipeline. And this is really where the magic starts happening. This is where you're actually sending out predictions to your real-time services on the far right. So now you have events coming through one of the data engineering components. And this is again where like the separation of concerns and roles is really important, is that, you know, we're creating a very simplified version of this, but a lot of what we do is actually on the data engineering side, taking that raw production data and raw events and perhaps rolling it up into complex queries and things like this in order to produce feature vectors that we can predict on with our validated model and publish that prediction. So without further ado, we're going to kind of close it off. But that's really what you want to start building, and then Dana's going to elaborate on some of the pieces that I touched on, which is especially validation, and how do you know what you've built is all the way back up to serving those objectives and part of the 15% of success stories.
Yeah. So what we're going to look at is really how to tighten up this process, because iterating on this, refining our pipeline, our models, is really key to success. And also, you know, as data changes, as our community or our systems change, we're going to need to train models. We do not want this to be a manual process or have a lot of manual steps in it. So testing of the model is so important, right? When you write code with logic in it, you have some idea that whether it might be right or not, because you understand the logic behind it, right? You know what's going on there. You know what you think you did. You think that's right. When it comes to training a model, it's largely a black box. You threw a bunch of data at it. It figured out something. It's going to output some results when you put something in. Maybe it outputs approve or deny. How do I have any idea whether that is right or not? And this is really the evaluation process that's going to need to tell you how good that model is. Now, of course, you know, we don't expect it to be perfect, but what we want to do is have a process that's going to ensure that as we make changes, we're actually making improvements. So we want each model, it's only going to go forward if it was at least as good as the last one. And automating that process is important. But there's a whole lot of other testing that's also really beneficial here. So there's a whole lot of machinery and logic around just that training process that if we get that wrong, if we make some changes, if we make some tweaks to make some improvements, and we don't have testing around that, we can easily go terribly wrong and take quite a while to figure out what's happened. So even testing our data, are we getting drifted in data? Is the nature of our production data changing in a way that is going to really necessitate us retraining our models? The data models that we take out of the raw data, we sort of roll up that raw data. We want to make sure that as we refine that process, maybe we're adding new features, whatnot, that we have tests in place that are going to ensure that we're still getting what we expect. And again, these tests are not necessarily the same as unit tests where we know exactly what the answer is. They may need to be more statistically driven, that we're expecting that the mean of this is not going to be terribly off what it was before, but we are making some changes, so there is some intent that the data changes a bit. And the data pipeline in itself, right? You need to test end to end that this thing's going to go through so you can make those changes with confidence. You should be applying version control to all those bits of code in there. So the tuning of the learning algorithm, any sort of hyperparameters you have in there, it's really important to be able to go back. If you had something that was working great 3 months ago, and your process for publishing these models is emailing a pickle file to somebody who's no longer around, you've lost that model, right? So retaining not only the results of that process, but the inputs of that process, and being able to post-mortem figure out what's going right, what's going wrong, having full access to that, along with all the transformations along the way. And really, where you want to be aiming for is really DevOps for data. So you want really a version-controlled process around your machine learning that's reproducible as much as possible, right? I mean, there is some random factors involved in the training, but outside of that, I mean, we want it as reproducible. We want to know what the inputs were to that. And then part of that process, if we make a change, let's say to our logic for extracting our features, we want not only those tests to kick off, but all the downstream dependencies to kick off tests and potentially get down to the point where we really have CI/CD for machine learning, right? I make a change, I commit that change, the tests happen, and things just chug down the chain. As long as all those tests pass, my model goes into a Kafka pipe and into production, and it's live. So let's wrap this up. There's some key actions here that are important. Really understanding and aligning on that solution. I think that getting a sense of what the events are, really aligning the whole team on the events through an event storing process is actually really valuable. Having as many perspectives on that data and understanding on the relationship between events. What does a different sequence of events really mean? How do I interpret that in terms of mapping that back to the business is really helpful. Event-driven systems then help to keep that fidelity between the business logic, which we have modeled in terms of events, business processes in terms of events, making sure that that carries through the application layer and that we get that level of fidelity in our analytics data and get some high-quality data to work with. Understanding all the process, the handoffs, like I said, knowing what you need to know and knowing what you don't need to know so you can focus on the task that you need to do, really critical. And lastly, that testing process and automating that testing so that you can really churn through this and you can make changes very quickly and with confidence. So this whole thing, I mean, it's not easy, but it's certainly not magic. And you can really only manage the things that you can measure, and you can really only measure the things that you're aware of in the process. And lastly, if you come from an application development background, maybe you don't have higher mathematics knowledge, there are so many opportunities to make significant contributions here. That should not be a barrier. Not that I would discourage you from learning about that. It can be a great gateway in, but don't let that be a barrier to becoming involved in that.
So thanks for coming out, everybody. We'll take a few questions, but this is us, Dana and myself. We actually also have a booth. The company we're with is Red Elastic. We're a consulting company based out of Toronto. So if you stop by, let us know, and we'll get you some coffee. So thanks, and I think we'll take some questions if anybody has any. Yeah, if you could use the mic, that'd be great.
Hi, thanks so much for the presentation. It was really informative. And I wanted to know, because you talked about the handoff between data scientists and technical engineers. Particularly at this conference, most of the technical engineers are going to be working in probably Scala or something in the Reactive framework. But primarily data science is still happening in like R or Python primarily. Do you view that as, I mean, the way you describe the handoff as just being this model is great, but do you view that as a risk at all, or do you see any movement happening to bring those two technologies together?
So, for one, if you're using Spark, MLlib to generate your models, those actually will work across different languages. So you could train in Spark in Python and then serve that model in Scala if need be. There are also some other solutions to serializing models like MLeap that will allow you to say train your model in scikit-learn in Python and then actually evaluate it using Spark machinery or otherwise. The other area that handoff and translation needs to happen is on the feature engineering side and the code to actually take maybe our raw data and extract out those features that are relevant. There are some options around there. I think Spotify had Featran.
Yeah, they had a really good one.
That is quite interesting.
I forget the name, but take a look
Featran, I think it was. Yeah, that allows you to do that feature transformation in a language independent way.
So yeah, I think tool selection, it's a great question. I think it's aligning with, again, it's the skill sets on your team. So, sometimes what we might even see if the data science team are all Python developers, perhaps there are Python skills also on the engineering team, even if you want to translate that code into Scala. But otherwise, there are definitely some options to avoid probably what you really don't want, or to be handed off Excel files as much as possible. So maybe we'll align on that. Any other questions? Great.
Thank you. It was a wonderful talk. And here I have a couple questions regarding the event and the model serving. The first thing I have question is, because the event come in row if we want to make real-time decision. And if its raw data is not processed, how can our model serve it? Another question is, can you give some recommendation about exporting the model? Because so far I don't see any tool, only deep learning 4J, except deep learning 4J if it's rule-based. I know Dual Rule Engine provide PMML, but in Spark, there is no public version of exported model as PMML.
So maybe I'll take the first, which is the events, yep. Raw events too. Yeah, that's a great question. So what we do sometimes actually also embrace the principles of DDD and eventual consistency and things like this. So we've actually used streaming to, especially if you go through an event storming session, you can actually build up application to sit in front. Like let's say you have raw events, but really what you want to do is output feature vectors based on a live business domain. You can actually build out, we've actually put ACA in front here and actually had actors representing all of the different aggregates within bounded context and things. So effectively, you have events coming in and you have a live domain model, and then you're basically just emitting feature vectors from that. So that's one reasonable way. It all depends on the latency requirements you have, because otherwise you're right, there could be some fairly complex roll-ups that would have to happen. Like let's say you have an event, you have to do a complex query to HDFS. You absolutely want to avoid that. So that's actually a real problem that we can see impacting. So there has to be some kind of pre-computation happening to go from raw events to feature vectors. And
Yeah.
maybe you want to handle that second. Yeah.
Yeah. I mean, to elaborate on that. I mean, yeah. So a lot of times, what's happening in that training process is, you're doing that extraction through big queries. It doesn't matter if they take half an hour to run to pull,
And even on
a
the
couple of
serving
millions.
side too. Yeah.
Yeah. And then just turning it around. So I believe we had a slide there that was, that updating that profile, which would, normally be, let's say, a great big SQL query, maybe to generate profiles for a whole lot of users, and turning that into a streaming process that's being continually updated, essentially, turning it into a materialized view happening through a state machine, right? So in terms of, your second question, I believe, was around model serialization, right?
Yeah.
And PMML. So MLeap there is a solution as well. I believe there are a few options for PMML in particular to go to
So far, PMML and libs there, but you can include the PMML, but you cannot explore from Spark itself.
Oh, yeah.
So-
Actually, I'm not sure of any solution for exporting PMML specifically from Spark. MLeap might be a good alternative there. And actually, MLeap goes a little bit farther than to just the model to the larger ML pipeline. So feature transformation in that, it can be a pretty good option.
One more question.
Hmm?
So regarding the model, when we do the prediction in the models, oftentimes the model is complex. So do we have any good solutions when we quickly deploy a model, but when we do the prediction, we can explain the model? Because a lot of times the model itself is hard to explain, and especially if I have a customer, I say you have problem, but I couldn't explain to my customer like you have a problem because of this event, but
That might be
Yeah.
a little bit of a bigger topic.
That certainly is
How
a bigger
about
topic.
this? Let's
Yeah.
take it offline and we'll have a coffee and talk about it. But thanks everybody for coming, and feel free to talk to us at our booth.
Thank you.